I was working with some devices fairly recently and just checking some of the I/O registers and trying to trace some data that was giving us some issues. And I came across something kind of interesting, a negative zero in one of the registers, and then found there were several others around. That's kind of cute. This is old. And the junior automaton with me is looking around. What are you talking about? We've got negative zero. This thing uses one's complement. What are you talking about? Well, two's complement is the more modern way of storing data. You don't end up with the negative zero. And it turns out he had absolutely no idea how negative numbers in binary systems work, and that's all right. And so, without further ado, today let's go ahead and talk a little bit about two's complement. Hello, welcome to Chaos and Controls, a show where we talk about modern devices, technologies, and techniques for automating your home business or life. I'm your host, the Automation Doctor. Jumping right into it, if we want to talk about two's complement, it makes sense first to talk about some simple addition. You may have heard that in like a computer, everything is addition in disguise, and there's some level of truth to that. That most things we can add to a computer, but if we can save on having to add additional things that the computer is capable of doing, we like doing that. So, by and large, sure, addition is a very common thing that we do inside of a computer, and we have plenty of interesting ways that we can help that do things other than just addition. But to start off as an example, hopefully it's of no mathematical ridiculousness for anyone here to add 4 and 2. Should all be aware that we get 6. And if we wanted to be a little more technically accurate, we could go ahead and add the subscript 10 to indicate that we are talking about base 10 numbers here. Base 10 just means that, counting numbers like you and I, 0 through 9. If I wanted to represent this in binary, hopefully you recall from the binary video, I could show with subscript 2 the binary strings here, and we're doing the exact same thing on the left-hand side as we are on the right. Still nothing goofy. If I wanted to subtract these numbers, I could do the exact same thing. The subtraction works the same way it has since grade school, and still, nothing of particular interest here. But where we're going to start doing a little bit of a departure, hopefully you agree with me, and going back to in the computer, we want to try and keep as much doing addition as we want. We don't want to have to add subtraction circuits. We want to continue using the addition circuit. And so instead of using 4 to subtract 2, we could actually take 4 and add negative 2. Right now, I'm just using a sign convention on the binary to indicate that this is a negative number. And so still nothing spooky here. Now what happens if I start with the 2 and I subtract the 4, or I add a negative 4, now we end up with a negative number. Still nothing spooky yet, but you'll notice that in the binary, I am putting a negative on the front of the binary. Well, in the computer, we can't store a positive and a negative. Everything's a bit. But I would bring attention to the fact that it's either positive or negative. There's only 2 of them. It's on or off. It's true or false. It's positive or negative. It's 0 or 1. So let's talk about two's complement. And two's complement is the method that we can actually store negative numbers in a computer system in such a way that you can just add them together and not have to do anything else funny. With two's complement, we make the statement that in order to make a two's complement, you invert each bit and you add 1. We'll do a couple of examples here. Never mind how they came up with this. Never mind, somebody far smarter than me sat down and went through all the math and figured out that this was an excellent way to do it. And we'll go through some of the benefits of getting to this. But just to take an example, if I had the binary value of positive 1, and I wanted to make this a negative 1, so two's complement takes you from positive to negative. And so I would invert all of the 1s, just like you see here, and add 1. And so positive 0001 in base 2, 1111 in base 2, this would be negative 1 in a two's complement system. And why would we want to do it that way? We'll get to some examples here for why that works out very well. It's worth noting that in a binary system where we have negative integer representation, going back to, the positive, negative sign, it's a 0 or 1. We assign the leading bit to indicate whether or not it is positive or negative. So this 0 over here indicates that we're positive. This 1 over here indicates that we are negative. And when we're looking at a negative number in 2's complement, it's kind of like an encoding scheme. You can't just add this, because this would be negative 111 would be 7. This is not negative 7, it's negative 1. So let's look at getting the reverse case of that. So I tell you that this is negative 1, and we want to see, okay, well, what does that look like? Well, we take the 2's complement to get back to the positive number. So I invert everything, 1, 1, 1, 1. Hopefully you agree all inverts to 0, 0, 0, 0. Add 1 just gives me 1. So the 2's complement gives me from here to here, but it also gets me from here back to here again. And that's the beauty of 2's complement, is that it actually can go both directions. We're doing the same operation to get the numbers in and out of the negative typing. So let's look at another example, a little more interesting one. You might ask, well, what happens to 0? Because at the beginning of the video we talked about, an older version called 1's complement. You had positive and negative 0. Well, if I start with all zeros, I invert and add 1, you'll notice I still end up with extra zeros. And you might say, but Doc, there's a leading 1 out there in front, and I've drawn this little line right here. If we are working with 4 bits, that's all the computer has is 4 bits. And the same is true if I go up to 8 bits, to 16, 32, 576, whatever I've got on the number of bits. If I have to add a number and it goes beyond the number of bits that I have in the computer, it might as well not exist. The difference between computer science and just working with normal binary. And so yes, there is a leading 1, but the computer has no idea it's there, and we're left with 0, 0, 0, 0 again. And so the next one that you might ask is, is equal to 0 in base 10. But another question you might ask is, well, so if negative 0 is this 1, 0, 0, 0, what would that end up getting us? And if we invert everything and we add the 1, this is a nuance in 2's complement. And please try to pay attention, make your peace with it. I'm probably going to gloss over some of the finer points here that are the real getches. But so we don't have a leading 1 or anything out past these 4 bits. And ordinarily, we said that this first bit is really the sign, but because we just took the 2's complement to look at what this thing looks like, we started with a negative over here, and so I know that in regular binary, this is equal to 8. But because we had the leading 1 and we took the 2's complement, we know it's actually negative 8. It's subtle, it's nuanced, and it's a gotcha, and a lot of people will struggle with that, and hopefully I'm doing an all right job going through this. And so you might ask, okay, so that's interesting. Can we do positive 8? And turns out, well, no. The largest number we can represent on the positive, and when we have a leading 0, we don't have to do any 2's complement, because 2's complement gets us in and out of negative. So we have a positive, and 111 gives us just a 7. We dropped the negative 0, and just as a consequence of 2's complement, it ends up as an additional negative number. And so we go from, in a range of 4 bits, we can only go from negative 8 to positive 7. We can go from negative 8 to only positive 7. And that's kind of interesting. Certainly probably would have been a little more useful if we had gotten an extra positive number out of it, but that's just, wasn't in the cards for making the math work out well. And so if you jump up to 8 bits, if you go look and what are the range of an 8-bit signed integer number, Google will tell you it's negative 128 to positive 127. I always get one additional negative number because we dropped the negative 0, and just as a consequence of how the math works out, it always ends up on the negative side. 16 bits, same thing, 32,768 to positive 32,767. So the larger your registers, the less of an effect it has, but still nonetheless, you always end up with a single extra integer on the negative side. So let's go ahead and look a little bit more into the math of how we would do something like 2 plus negative 4, because going back to in the computer, we can't have this sign out in front. And so we need to take a 2's complement of my negative number. And the 2's complement, if we invert everything and add 1, hopefully you will agree that we end up with this 11000. And now we can just do regular binary addition. 0 and 0 gives me 0, 1 and 0 gives me 1, 0 and 1 gives me 1, 0 and 1 gives me 1. And this is how the computer is going to store that number. However, if I want to know, well, what is that number, we look at the leading one, say, okay, it's negative. So in order to see it in regular binary, we have to take the 2's complement. And the 2's complement takes that to 0010. And hopefully you will agree that that is equal to 2. But we had a leading 1, so we know that, okay, this is a negative number. We take the 2's complement. That number is 2, so it is a negative 2. And hopefully we still all agree that 2 plus negative 4 equals negative 2. There's a lot going on here. It's kind of a confusing topic, particularly if you are more accustomed to conventional mathematics and not the computer science side of the house. But it's very well worth noting. And it's also just a cute trick you can have to torture your junior automatons when you're out and you come across a negative 0 on something and they've never heard of 2's complement. That's about all I have for y'all today. I hope you have a good one. The eclipse is coming up at the time of this recording. Hopefully that all goes well for everybody. I will catch you next time.